Good afternoon and welcome to the EPA Alumni Association Academy's program on the Polar Vortex. Nature has provided us a lot of free publicity for this program. I wish to thank Dr. Jennifer Francis and Dr. Judah Cohen for appearing on today's program. Their willingness to do so and cooperative spirit have made my life much easier. Both are well recognized in their field and have made numerous public appearances and have appeared quoted in the New York Times and the Washington Post on the polar vortex. After their presentation, there will be a question and answer period, and I ask that you put your questions in the chat, and I will read them to our participants. Dr. Judah Cohen is a research scientist in the Civil Engineering Department of MIT and is director of seasonal forecasting and principal scientist at the Janus Research Group. His research interests include polar vortex, Arctic mid-latitude linkages, and extreme weather. Seems like meteorologists always are interested in extreme weather. He is developing seasonal forecast products to predict weather 3 to 6 weeks in advance. The current forecasts are really, if you notice on your TV meteorologists, are only about 10 days max. Dr. Jennifer Francis is a senior scientist at the Woodwell Climate Research Center in Falmouth, Massachusetts. She was a professor for 24 years at the Department of Marine and Coastal Sciences at Rutgers. She and her husband sailed around the world, including in the Arctic region, which is what piqued her interest in the Arctic. Both Dr. Cohen and Dr. Francis were co-authors on a paper in Science Advances in 2025 entitled Cold Air Outbreaks in the Continental United States, Stratospheric Variations. So here is Dr. Francis.
Okay, I'm ready to go. Hey, everyone. Thank you so much for tuning in. As Gary mentioned, we couldn't have had better publicity from Mother Nature herself, creating this extreme winter weather event. So we will try to put that into context for you, explain how these sorts of events are created, and how climate change is perhaps playing a role in affecting their frequency, their intensity, and generally how they are evolving with time. So here's my slides coming up here. All right, so as those of you east of the Rockies know well, it's a little chilly out there, and this plot here is showing the temperature differences from normal for basically today, yesterday time frame. Of course, the purples and blues are where it's colder than normal, and the reds and yellows are where it's warmer than normal. So we've heard lots and lots in the headlines about the cold and the snow, but what you haven't heard is that always together with a very cold outbreak like this, we always see the opposite on either side. And that is something that gets lost in the messaging, I think. As you can see on this diagram in the background here, the entire western states of the US and Western Canada are bright red. It's much warmer than normal there. In northern Canada and up into the Arctic, you can see it's also very warm there. So it's these differences and contrasts that are all connected, and that's what you're going to be hearing about today. So my talk is going to be focused on more the background, and then Judah is going to take over afterwards and really dig down into the details of the stratospheric polar vortex and how that is behaving and changing. So when we talk about a recipe for an extreme winter weather event like this, really the main ingredient is always going to be the jet stream. And you can see that I have an S after that. There are actually two jet streams oftentimes in the winter. This plot here goes along with the temperature anomaly plot that I just showed you. And so what you can see is these bright red and purple colors here are where the winds of the jet stream, which is up at altitudes where jets fly. You can see where the jet stream Z is right now. And what you notice is there's this big northward bulge. We call that a ridge over the western states, and the big southward dip or a trough over the eastern states. So you can see that, as I said, there are these two jet streams. This one is called the polar jet stream. Some people also call it the tropospheric polar vortex. I find that extremely confusing to people to have two polar vortexes being discussed. So I always just call it the polar jet stream or just the jet stream. And what Judah's going to talk about is a completely different thing, as I'll show you in a second. But also what we have on here is the subtropical jet stream. And this is another fast-moving river of wind that is higher up in the atmosphere than the polar jet stream, but not as high as the stratospheric polar vortex. So sometimes in the winter, we have both of these jet streams happening at the same time. And when they converge, like they are right now off the East Coast, this is when we tend to get our biggest coastal storms. And you can see that's what's happening right now. So both of these jet streams really exist because of temperature contrasts. In the case of the polar jet stream, it's the very cold Arctic air to the north, contrasting with the more temperate air in mid-latitudes. Whereas the subtropical jet stream is the boundary between the very moist, hot tropical air and that temperate air in mid-latitudes. The jet streams really do create and steer almost all the weather that we experience in the Northern Hemisphere, except for hurricanes. And it's really these waves in the jet stream that we talk about when we think of high pressure and low pressure areas that you see on a TV weather map are associated with these ridges and troughs in the jet stream. So you can see a high marked here where the jet stream is out of the northwest, and this big storm that we just experienced in the east exiting out to the Atlantic, associated with the southwest flow of these waves in the jet stream. So these waves are really, really important in the jet stream. And as I said, in the wintertime, we often see both the subtropical jet and the polar jet, but not always. And there are many, many factors that can affect the jet strength, its position, north and south, and the position of these ridges and troughs, and how big those ridges and troughs are. So there's a lot to talk about. I'm going to try to boil it down into just the main ingredients in this recipe for extreme winter weather. Now, as I already mentioned, we really care about these waves because they do create the high and low pressure areas that we experience here on the surface. So as I already mentioned, here we've got the polar jet in a very schematic form here. As you can see, and as I already said, it really divides the cold air to the north from the warmer air to the south. So when the jet stream is south of you, which is the case right now for most of the east, all of that cold air has been allowed to plunge way far north, all the way down to the tip of Florida. But in these parts of the wave, we see this northwesterly flow in the ridge part of the wave associated with dry and settled weather, high pressure, and the southwesterly flow is where you typically find your storms. And so these waves in the jet stream have everything to do with whether you're experiencing dry, sunny weather like the western states are experiencing right now, or whether you're in a stormy pattern, and then the position of the jet relative to you determines whether you're in a colder or warmer air mass. Now, these waves are also important in terms of their size, because when there's little ripples in the jet stream, they tend to move really quickly from west to east. And that's what we would experience on the surface as being rapid changes in weather. A couple of days of nice weather, then some rain or snow, and then a couple more days of nice weather again. But when they get really large like this, which is the case right now, they tend to be very persistent. They move very slowly from west to east. And so we tend to be in these very persistent weather regimes. And that is indeed what's been happening pretty much since December, not constantly, but a lot of the time we've been in this kind of a pattern because this wave has been so persistent and so large. So what other ingredients affect the jet stream? Well, and is human-caused climate change affecting the recipe for these winter extreme events? Well, spoiler alert, yes. And we're going to talk about what some of those ingredients are and how they might be changing. So the first one I want to mention are marine heat waves. What we're looking at here are the temperature differences from normal a couple of days ago for the whole world. You can see that there are areas of blue where it's colder than normal, but most of the northern hemisphere is dominated by red colors, which means the oceans are warmer than average. And in particular, what we notice is this blue area off the coast of South America, which we know is a waning La Nina. It used to be that La Nina and El Nino were kind of the only game in town when it came to trying to predict seasonal weather. But now that we're seeing these very potent marine heat waves dominating the northern hemisphere oceans, really their influence is overwhelming La Nina in most cases. But what La Nina does do is, you remember, the jet streams are affected by mainly changes or differences in temperature between locations. Well, when you've got cold water sitting off the coast of South America, what that tends to do is weaken the north-south temperature difference, and that tends to weaken the subtropical jet stream, and that's why we generally expect drier than normal conditions across the western part of North America. But let's get back to these heat waves. So we've got a really big, strong one up in the northwestern part of the North Pacific Ocean. That's been there for literally weeks, maybe months. We've got another one sitting off the coast of California and Mexico, the West Coast, and we have another one sitting out in the Atlantic. These have all been very persistent. And what they do is they warm the air above these heat waves, which creates sort of a heat dome in the atmosphere, which tends to shove the jet stream up and over them. So thinking back to the waves that we are experiencing right now, what we can look at is, just based on where these heat waves are located, I could sketch what we'd expect the jet stream to look like in response to these marine heat waves. And indeed, it looks a whole lot like what we've got right now. And it's the fact that these heat waves are so persistent, they last for weeks and sometimes months, they tend to set up the position of the jet stream over a long period of time. And another way to think of this is, what goes up must come down. And so when we've got a heat wave here bulging the jet stream northward, we almost always see a big dip in the jet stream to the east. And that, again, is what we're seeing. So these marine heat waves also increase the amount of evaporation of moisture from the ocean into the air. And of course, the air is warmer too, so it can hold more moisture. And one of the I think underreported aspects of the climate crisis, climate change, is this big increase in atmospheric moisture, the amount of water vapor in the atmosphere. You can see, going back to 1940 here, we're seeing a very impressive and strong increase in the amount of water vapor in the atmosphere. That does a lot of things. That water vapor is a greenhouse gas, so it's making the heat trapping aspect of the atmosphere even stronger. That moisture is fuel for storms, so it's actually leading to storms being stronger when they do form. Think hurricanes and nor'easters, any kind of storm. And of course, when there's more moisture in the air, when a storm does form, it has more water vapor to work with to turn into precipitation. So we're seeing heavier downpours, heavier extreme precipitation events, and even heavier snowfalls when it does snow. So that's another important aspect of what's changing in the climate system and how it's affecting our weather. Another ingredient is the rapid warming of the Arctic. And looking down here, we're looking at just the month of this past December and the temperature differences from normal across the Arctic. So the North Pole is right in the middle here. These red colors are 3 to 4 to even 5 degrees warmer than they should be for a normal December. This region north of Scandinavia here is called the Barents-Kara Sea, and Judah's going to talk a lot about how important that extremely strong warming is in that part of the world in influencing the stratospheric polar vortex. But overall, we notice that the Arctic is warming much faster than the globe as a whole. This is known as Arctic amplification or amplified Arctic warming. And this is a big deal because if you think back to why the jet streams exist in the first place, it's because of the differences in temperature between the north and the south. And so if you're warming the Arctic much faster than the globe as a whole, it means that that north-south temperature difference is getting smaller. And that means that the winds of the polar jet stream are getting weaker. And we know that when the polar jet stream is weak, whether it's through Arctic amplification or just natural variability, we know that we tend to see the jet stream take bigger swings north and south, those bigger ridges and deeper troughs. And that means that the weather regimes that we are experiencing are probably going to last longer. Then finally, this is what we're really here to talk about, is this contribution by the stratospheric polar vortex. So let's make sure everybody knows what the polar vortex is before we get into how it's changing potentially and how it influences these extreme winter weather events. So just looking at this diagram, the light blue here is the polar jet stream that we've been talking about mostly. Also, as I said, sometimes called the tropospheric polar vortex, which I do not like that term, so I always call it the polar jet stream. It's always there. The jet stream is always there. Up farther north and higher up in the atmosphere is another very cold pool of air. It's much higher up, and this is the stratospheric polar vortex. It's only there in the wintertime. It doesn't exist at all in the summertime. And most of the time, it sits up there and it really doesn't affect our weather too much. When it's very strong, like in this diagram, we tend to see the jet stream shift northward, and we tend to see more mild winters experienced in North America and Europe. But occasionally this stratospheric polar vortex becomes disrupted. Instead of being tight and circular like this, it can stretch into a bean shape. It can even split into separate circulations. And when this happens, we know we tend to see some pretty wild winter weather happening all around the Northern Hemisphere. And that is what Judah is going to be talking about. So this is an animation showing a splitting of the stratospheric polar vortex. And I am now going to pass it over to Judah to go into much more detail about the stratospheric polar vortex.
All right, thank you, Jen. Hope everybody can see my screen. Yeah, so, and thank you to, I guess, EPA alumni for this opportunity. Just make sure I got the laser pointer on here. So yeah, so we've, as Jen was pointing out, we've seen strong warming in the Arctic. And this winter, we've also seen with that strong warming in the Arctic, very cold across the continent. So I assume pretty much everybody here is in the US, so we're familiar with the cold air in the US this winter, but it's been in Canada as well, and even across large parts of Europe and Asia, especially as of late. And this was kind of been labeled the warm Arctic, cold continents pattern, and it's been a strong debate. Are they kind of just coincidentally related? So that that they're not physically connected, or they're causally related. And I think I speak for Jen too, but certainly I'm very strong belief, and wrote many articles making the argument that there is a relationship, and that relationship goes through the polar vortex. That's that kind of physical pathway or the bridge that when you get this warm Arctic, it does favor this widespread cold across the continent. It's not ever always, but many times. And as was mentioned before, the weather has certainly cooperated in getting people's interest in the polar vortex. There's a bunch of headlines. You can see many all of them. I think I had the polar vortex in the title, especially late with the cold, and certainly once you get a big snowstorm, that really gets everybody excited. So I'm going to try to very briefly in the time that I have, make the argument that Arctic change is contributing to an increase of these disruptions of the polar vortex. Jen kind of showed an example of a split polar vortex. But there's something I think was very underappreciated, another kind of behavior or mode or flavor, if you like, of the polar vortex. And this is where it stretches out or elongates. And I'll try to explain why I think that's of particular importance for this discussion of maybe Arctic change and how that's influencing the polar vortex, and especially might be influencing our weather here in the United States. So Jen talked about this. I won't get into this detail, but yeah, to be clear, there's I think confusion maybe the way the media talks about it. Polar vortex, it has been often become synonymous with cold air outbreak. So, they're not the same thing. The polar vortex is way up here in the stratosphere. So if you think of the atmosphere having two layers, the bottom layer is the troposphere where we live, the weather occurs, and then above that is the stratosphere, and that's where the polar vortex is. But then, as Jen again said, so just it's in high altitude, but in high latitude as well. The jet stream tends to be further south, and it's obviously lower. It's in the troposphere, and it tends to be a lot wavier than the polar vortex. In its normal state, the polar vortex is pretty circular. So here's an animation of what's going on, has gone on with the polar vortex since the beginning of winter till pretty recent. And hopefully you can, so here's this low L, this red L is the center of the polar vortex over the North Pole. And hopefully you can see this. But the polar vortex has kind of been alternating between where it gets kind of stretched out, elongated between Asia and then Canada and the US, and then other times where it becomes more circular in shape. So here you can see a very nice, I think, a stretching, and that's going to become more circular, and then we'll stretch out again. So I've been calling this pattern rinse, lather, repeat. Last winter was the same thing. We'd have a polar vortex stretch, it got more circular like it just did there, and now it's stretching out again. You can see it stretching out here in the second half of January, and that's been leading to or it's certainly associated with all the severe winter weather we've seen east of the United States. And here I'm showing three different examples of, I think, the really important modes or behaviors of the polar vortex. This is from the January, February 2020, 21, December, January, February 2020, 21. So right at the beginning of the winter, we had a strong polar vortex that was circular, was relatively mild across the U.S. We had strong, what we call zonal flow, maybe when those waves that Jen was talking about are kind of damped or not amplified. It's called zonal flow, so the wind's west to east. So we get our source of air across North America, or certainly the United States, is from the Pacific, which is mild. Then there's this in mid-January, there's a very large disruption of the polar vortex. We call that a sun stratospheric warming. But purpose of that's just the largest disruption of the polar vortex. It gets quite distorted. So this here is not the polar vortex. That's high pressure, the Alaskan high pressure that you see in the climatology. But the polar vortex is kind of split in two pieces. I don't know if this is probably not really a split, but there's one here over the Barents Sea near Scandinavia and northwest Russia. The other one is here in kind of Canadian Maritimes. And that's what's been mostly studied. 99.9% of the studies have been on these very large polar vortex disruptions. This is what's really the focus of my talk. Then in February, polar vortex is here near Greenland. And so again, it takes on that stretch elongated configuration or shape. Here's that Alaskan ridge near Alaska, fittingly. But what's really important is that, like all low pressures in the Northern Hemisphere, the flow is counterclockwise or around low pressure. So you have a very strong flow from Siberia across the Arctic and down Canada into the United States, east of the Rockies. So the fact that it's grabbing air from the coldest region in the Northern Hemisphere, really the world at that point, from Siberia, and quickly delivering it into the United States. So it has less time to modify. So you get these really extreme cold air outbreaks, just like we're experiencing currently. And we're going to see record cold temperatures despite how much warmer the globe is. Again, this is in the stratosphere. That's not where we live, not at the surface, not with the weather, but they tend to, the jet stream tends to mimic what happens with the stratosphere. And so how do we connect this to Arctic change? So everybody knows that Arctic sea ice is melting away. There's much less ice, but it's not uniform or homogeneous across the Arctic. There's heterogeneities the region that is where it's melting the fastest is called the Barents Sea. So here's Scandinavia, so kind of between Scandinavia, this is St. Joseph's Land, but northwest Russia. That's the area that has seen the biggest sea ice melt. But I think something that I think it is important to this whole story. It doesn't get as much attention. There's been more snowfall in the fall and winter months, especially across the high latitudes, so including Siberia. So I think October is a key month. There's been an increasing trend in snow cover, not just snowfall, but snow cover across the high latitudes. Both continents, so both across Siberia, but also in Canada. And I think this is contributing. I'll try to discuss why. So it's maybe the most technical part, but Janice talked about waves. So she talked about this ridge of high pressure across North America, but there's the same wave occurs across Eurasia, but it's much larger. So you tend to have a ridge of high pressure across northwest Eurasia, so kind of near Scandinavia. And then you have this very deep low pressure troughing across East Asia. So just like that kind of roller coaster shit that Jen described, have across Eurasia. So it goes the areas of low pressure or temperature, if you follow them, it goes way to the north across northwest Eurasia, across UK, Scandinavia, and then it dips way to the south. Certainly as you get into this coldest area of the northern hemisphere across Siberia. And if you look at a kind of anomaly sense across, you take away the zonal mean, you can see that you have two big waves in the atmosphere. There's that North American wave, so the ridge to the west, troughing to the eastern kind of eastern west. But I mean, the Eurasian wave is so much bigger in size, and this is important. But again, that ridge of high pressure to the west and that low pressure troughing to the east. Right. And so I kind of drew in by hand across the Eurasian continent here, that where it goes way to the north across the west and tips way to the south. And again, what's happening with Arctic change? Sea ice is melting across this Barents Sea, northwest Eurasia, Scandinavia, northwest Russia. And that high pressure ridge is like pumping air into a tire, right? So when you pump air into a tire, it's supported by the warming of the air. So if you're losing sea ice and all of a sudden this ocean comes in contact with the atmosphere, large amounts of heat are escape into the atmosphere. That's kind of really pumping that atmospheric tire, to sort of speak, but you're really pumping up the ridge. So it's getting even more amplified. And then more snow, that leads to colder temperatures. So that's like letting the air out of the tire. If you put your hand where the air is coming out, it gets cold. So as you're cooling the air, you're deepening that low pressure troughing. So this Arctic change is really amplifying this kind we call a standing or natural wave across Eurasia. You have a bigger wave. And here's looking at the geopotential heights, or kind of the pressure surfaces at the jet stream level. So red means there's higher pressures, higher geopotential heights across in that same region, that Barents Sea. This is trends for December. But there's also this deepening of this low pressure troughing. So you really see how, if you look at this December trends, it's really amplifying this standing wave across Eurasia. And that really sets the stage for what happens with the polar vortex in January and February. So here's a schematic trying to bring it all together. So before we had Arctic change, we had this natural standing wave across Eurasia, mostly warm to the south, colder to the north. Here's the polar vortex above that. This dashed line is meant to represent the jet stream again, lower in altitude and lower in latitude. But the polar vortex tends to be in its normal state, circular and strong. But there are these waves now coming up from wave energy, just like ocean waves give off energy, so do the atmospheric waves, but they also not only propagate horizontally, they also propagate vertically. So they try to reach the polar vortex, but if the wave is small, they don't quite make it there. Same thing, you see the jet stream crossing North America with its standing wave with that kind of ridging to high pressure to the west and low pressure troughing to the east. And again, that cold to the north, typically warm to the south. But with Arctic change, we're having now this warming is kind of getting moved around. So everything's relative, but get the strong warming, as Jen showed already, and I showed in my first slide, in the Barents Seas. you have the strong cooling in Siberia because of the more snow. And now that standing wave is being amplified more often, not always, but more often. And so you have a bigger wave, you have more energy, and that's going to disrupt the polar vortex. And we've found that the type of disruption that has been increasing the most is this stretching elongation of the polar vortex, like I showed in that animation. And then, so when that's happening, the energy coming out of Eurasia bounces off, reflects off the polar vortex, and heads back into North America, just like if we were standing in a cave and we were speaking to each other. That the sound wave would bounce off the walls, and you would hear it, and you'd hear echoes. Same thing's going on here with the energy in the atmosphere and bouncing off the polar vortex. That energy gets absorbed in the jet stream or the wave across North America. That gets amplified. So I mean, this winter, this January is a great example of it. Warm to the west, cold to the east. So that's kind of a schematic of how my argument and with my co-authors, how Arctic change is leading to change in the polar vortex that are so critical for, whether severe winter weather occurs or not. And to me, this is a very compelling figure. I guess I look at the polar vortex every day, all day long. So for me, I'm familiar, but hopefully this comes across. Here's the polar vortex, the climatology. So again, the low pressure center right near the North Pole. It's semicircular in shape. Here's that Alaskan ridge. And this blue and red shading shows how the variability has been increasing or decreasing. So it's blue means the variability is increasing. It's increasing in a line from Siberia into Canada and the United States. So it used to be that the polar vortex used to be stay more circular. It was kind of a more stable configuration. But in the period of Arctic changes since 1990, it's been stretching and snapping back. That is increasing. I mean, it's always occurred, but now it's occurring more often. And if you go through 2000, it's even more amplified, where that elongation or stretching into Canada, especially the US, has really increased over the past quarter of a century. And the past two winters would only add to this for sure. And when that polar vortex kind of heads south, so it brings with it the cold weather. Maybe kind of Santa Claus, Christmas bringing the toys to everybody in the United States. But here where the polar vortex is delivering colder in your stockings or cold weather, not the toys. And here's looking at, we use quickly this metric for looking at all kinds of severe winter weather. So an aggregated index. And so where it's blue, severe winter weather is increasing. Where it's red, it's decreasing. If you go back to 1950, everybody says it, the winters are getting milder, less severe, less snow. But starting in 1990, there's this blue shading started increasing. So here's that, the shading shows the variability in the polar vortex, that stretching. So wherever you see that there's more stretching into those regions, Asia and North America, you see this blue shading now. So as the stretching increases, so does severe winter weather in Asia, in the United States, not Europe. And then since 2000, I said how that stretching has become even more exaggerated or has increased even more. And you can see that increasing more blue shading, so more severe winter weather here in both Canada and the US over the past quarter of a century. And this paper that was mentioned, Gary mentioned right at the beginning, that just came out this summer. We looked at the severe winter weather for all kind of behaviors of the polar vortex. I really just wanted to show you here that when we stretched polar vortex, which is this P3, clustering, so both severe cold, extreme cold, and heavy snowfalls are most overwhelmingly associated with a stretched polar vortex. So that's what I really want you to take away from, maybe a little bit of a busy map. So what's going on currently? This is my colleague, Matt Barlow, drew this very nice graphic showing all the cold temperatures. You can see the jet stream in lighter blue, and then the polar vortex in this deeper blue. So really showing how they all come together here over North America. And you can see that we've had this more recent kind of shorter animation. But again, that stretching has continued. And it's really that stretching of the polar vortex, which shows on the graphic on the left and which you see in the animation, is really critical for this delivery of a severe winter weather. Again, for this winter, Here on the left, I show trend how much snowfall relative to normal, and sea ice here on the right. I just want you to focus here. You can see across Siberia has been way above normal snowfall, also Canada, but also that sea ice in the Barents Straits has been way below normal. So I think everything that I discussed is really consistent with what's happening this winter. And the proof is in the pudding, or the proof of the pudding is in the eating. One thing I do that's I think very different from the large government centers, NOAA, but also ECMWR, which is considered the best, is use Arctic predictors in making that winter forecast. Here's our forecast. Here's the ECMWR. You can see very warm, no cold weather predict below normal temperature anywhere. I mean, models were unconfident here in Western North America, but look how warm Eurasia was. And here's what's happened so far. A good part of the chunk of the winter's gone, and I'll show the forecast in a second. So I'm certainly feeling much better that showing this widespread cold in our forecast. And Jen and I participated in a forecast in November, so she could testify that I didn't just make this up yesterday or something like that for this presentation. So. And also, as Gary mentioned, I'm also, besides the seasonal forecast, I've gone into subseasonal, which is the 2 to 6 week time frame. And here's the model here predicting extreme cold in Canada and the northeastern US in December. And that did verify pretty well. And again, we put it on real time, and certainly got some attention in the media, especially this New York Post. They really went hyperbole on it, but certainly a lot of 11 million views on that one. So in summary, the world is warming, but the Arctic is warming 2 to 4 times faster than the rest of the globe. Jen said Arctic amplification, but this includes both melting Arctic sea ice and increasing snowfall in the cold months. Strong relationship exists between the jet stream and the polar vortex. Both can influence each other, and that relation could be modified by this Arctic amplification or accelerated Arctic change. I've been arguing for 20 years now, actually, that there exists a dynamic cooling related to more polar vortex disruptions that is offsetting this thermodynamic warming, especially Jen pointed out the very warm oceans. I showed some observational analysis. I didn't show model sensitivities, but there both exist that support Arctic change is resulting in more episodes of this polar vortex disruptions. And especially important, I think, for the discussion here, but I think for our weather in the U.S., these stretch polar vortex events, and then they cause regional severe winter weather. It's not hemispheric, but it's regional. Recent trends project onto patterns of variability related to stretch polar vortex events. I showed that in that one slide quickly. And then, using Arctic predictors has consistently led to improved long-range forecasts on the seasonal to seasonal horizon. An important I believe the most important, really, demonstration that Arctic change can result in episodic outbreaks of severe winter weather, and that pathway goes through the polar vortex. I think I was kind of in that 20-minute, so I'll just end what's going to happen. So here's that kind of an animation from today. So here's that stretching that's bringing the cold weather. But if I don't know if again, you'll have to take my word for it. This shows that polar vortex split. This one model is predicting that Jen showed in her schematic. So this is a much larger disruption than these stretch events, which tend to be much shorter in duration. They're not as dramatic in the stratosphere, as you can see here, these 2 centers being formed. But they are also associated with cold weather. Here's a forecast here, a 14-day forecast. I think that ends like February 20th or something. So that the beat goes on. So at least the models are saying the cold pattern is going to continue certainly into the second half of February. With really eventually this pattern will end and spring will come, but it's not. The models aren't showing an end just yet. So anyway, thank you very much for your attention.
Thank you, both of you. It was a very interesting presentation. There have been a few questions that have been posted in the chat, which I will read. It says, please mention the TPV, which is being mentioned in current weather discussions in the DC area. I think you may have covered some of that, but again, it might be worthwhile to mention it.
I'll give Judah's voice a rest. So I did mention that. So the TPV is the tropospheric polar vortex, which, as I said, I think is one of the most confusing terms out there, just because people only hear polar vortex. So I've been on a campaign to try to get people to say jet stream, not tropospheric polar vortex, and then reserve the term polar vortex for the stratosphere.
Sounds good. Another question, how does the situation in the Northern Hemisphere compare with that in the Southern Hemisphere?
I'm happy to jump in on that one too. The two polar regions are extremely different from each other. First of all, the South Pole region is a continent surrounded by ocean. So you've got the Antarctic continent sitting on the South Pole, surrounded by ocean. The Arctic is just the opposite. It's an ocean surrounded by land. The changes in the Southern Hemisphere have been much smaller up until recently. There has been very little melting of sea ice, for example. It's really only been in the last decade at the most that we've seen some sea ice disappearing from Antarctic waters. And the reason is because in Antarctica, most of that sea ice forms in the winter, and then most of it melts away during the summer. And so by doing that, you eliminate this positive feedback loop that is mostly responsible for the rapid Arctic warming. The reason this positive feedback loop basically involves sea ice in that when you lose ice, as Judah mentioned, you expose much warmer ocean underneath to the atmosphere. And that puts a lot of heat in the atmosphere. That melts even more ice, so it disappears even farther. More of the sun's heat is absorbed into the ocean, and you set up this vicious cycle. Well, because in Antarctica, that doesn't happen because you already lose all that ice in the summertime, basically. So you don't have an opportunity to create this positive feedback loop to any extent. So if anything, actually, the jet stream in the Southern Hemisphere is contracting closer to the pole. It's partly related to the recovery of the ozone hole. So there's just very different dynamics and thermodynamics happening in the Southern Hemisphere. So we don't see this kind of amplified waviness or changes in the stratospheric polar vortex that we see in the Arctic.
Yeah, I would just add one thing to what Jen said. The topography in the Southern Hemisphere looks like a donut or an annulus, right? So you have the continent right over the pole there, the South Pole, and then it's surrounded completely by ocean. So if you think of it as a donut or a zero wave, that means there's no waves. And what controls the polar vortex is how wavy the jet stream is. The Southern Hemisphere, because of the topography, tends to be not wavy at all. So it is very difficult for the jet stream to really disrupt the polar vortex. So the polar vortex in the Southern Hemisphere is much more stable and much stronger than the Northern Hemisphere. At almost always is always in this circular shape. It really, you don't get these very large. It doesn't stretch. As far as I know, too much. But some of these very large disruptions don't occur either. So that topography is very different. It's very critical. It's different. So Northern Southern Hemisphere, like what I described about the Northern Hemisphere, completely doesn't exist in the Southern Hemisphere.
Is the jet stream also speeding up?
Overall, no, just the opposite. And that's because of this weakening of the north-south temperature gradient because of the Arctic warming so much faster. There are certainly places where it's speeding up, in partly related to these ocean heat waves that are occurring. So where you have an ocean heat wave, you're actually increasing that poleward gradient. So there are places where if you warm it to the south of the jet stream, that makes the difference in temperature between that ocean heat wave and areas farther north even larger. So there are places where it's speeding up. But overall, we've been able to detect an overall weakening of the west to east winds of the jet stream, and that is at least partly related to the rapid warming of the Arctic.
Another question. Snow in the western U.S. is so important for sufficient water in the summer. Is there any hope that the snow drought in the west will change before winter is over?
All
Well,
you, Judah.
Okay, I'll grab that first. I mean, yeah, the pattern seems to have been stuck. I don't think there's great hope. I think the biggest hope for the Western U.S. is that we get this much larger polar vortex disruption. It's just more of a wild card. When you get a stretched polar vortex, it's not as dramatic, maybe not as much hype, but you're pretty, I mean, the impacts are pretty well confined, we know. But when you get a large polar vortex disruption, eventually it tends to lead to colder or snowier weather in the east, but not initially. So if we get a large polar vortex disruption, and you saw that in that last forecast map I showed, it showed the colder weather expanding. So more of the U.S. is covered in cold, but it does now include the western U.S. So I think, it's the models are disagreeing with each other what exactly is happening. But if we do get that larger polar vortex disruption, what's called the sun stratospheric warming, I think that's the best chance for some winter to show up in the western U.S., cold and snow, before it comes to an end.
We could also see a shift in the ocean heat waves in the Pacific. They do last a long time, but they do eventually shift. And that will allow a trough to form closer to the West Coast, which tends to bring Pacific moisture into the Rockies. But usually the snowiest time for the Rocky Mountains is in March, when you get some low latitude lows sucking in moisture from the Gulf of Mexico, and with a relative east wind driving that moisture up the mountainside on the east side of the Rockies and bringing snowfall there. So there's hope. There's hope.
When winter camping in Big Bend and Texas for the first time in the early 80s, we suddenly had cold fronts and ice storms sweep through. Your graphs show the vortex wobbling in 1990 to present. Is there any data that shows disruptions or on an earlier time frame?
Go ahead, Judah.
Yeah, with the sun stratospheric warmers, they really occur in January and February. As far as I know, they're not occurring earlier. But these stretch events, I mean, they happen soon after. They can start happening after the polar vortex forms in September. So that, I mean, this one paper that we showed this increasing trend. It was for the fall months. I do think November, for some reason, we have been seeing a pretty strong warming trend in December. This December turned out not to be that different, despite maybe what people's impressions were. But in November, there's been this increase in stretching events, and November hasn't been as warm. There hasn't been as strong a warming in the U.S. as December, which I find kind of strange. So again, I think stretching starts soon after. It's always started, but in November, it seems to me that maybe there has been this increase in the stretching in November, which can bring some colder weather a little bit earlier. So again, earlier. And this November also, people remember it was quite mild, and all of a sudden towards the end of November, it got very cold heading into towards Thanksgiving. So, but I'll leave it there.
Okay. What kinds of monitoring or instrumentation provides the data on the stratospheric polar vortex behavior?
I think the key is the satellites. The only reliable, and I'll jump in here, but Jen can add. I mean, so I think most of it's some satellites. There are these radio sondes they shoot up into the atmosphere, but reliable data of the stratosphere started with the satellite era in '79. So I think the satellites are the most important instrumentation for the stratosphere.
Okay. And they said that paleontologists have noticed that past records show climate change started with weather getting very unstable for some time. And then there is some sort of tipping point at which climate switched suddenly into being very warm. Do you think that this is coming to us?
Yeah, so this is not my area of expertise. I want to start out that I do think, so my argument heavily dependent on heterogeneous warming in the Arctic, if that warming became homogeneous, so if like all the sea ice melted or it melted equally everywhere in the Arctic, I think that could lead to a more stable stronger polar vortex. So we could see like a step up, a step jump kind of in the warming and winter months. That's as much as a tipping point. Obviously a tipping point, but
Right.
it's as much as I'll say. Did Jen disappear? I don't see her anymore on my screen.
I don't see her either.
Okay. All right.
Oh,
here she
there's
is.
Jen.
Sorry
It
about
must be
that.
frustrating for demonstrating global warming for decades, and still we are not doing nearly enough. How do your colleagues stay engaged with this work? Thoughts for us as an organization to be of help?
Well, I caught enough of that. I think I can answer. So what gives me a lot of hope is that even though things are rather upside down in Washington, D.C., at the community, state, county levels, there's so much going on, even in red states. We're seeing a lot of new solar and wind, renewable energy coming online. We're seeing a lot of action along areas that are really vulnerable to various risks owing to climate change, especially these extreme weather events of all sorts, but even these winter events. We see that Texas learned a lesson back in 2021 when they had that really extreme cold spell and ice storm and so forth. So they did a much better job this time around. It's not great, but it's better. So that's what gives me a lot of hope. Washington seems to be doing everything it can possibly do to get in the way, but I think a lot of people realize this is a huge problem and doing a lot of great work to get us at least to a place where the future won't be as bad as it could be.
It's very kind and encouraging. What is a bomb cyclone? As one question.
Yeah, okay. So I mean, the media likes to find buzzwords to get people's attention. I mean, obviously, the polar vortex is one, started in 2014, and before I become critical, I've certainly tried to piggyback on that. So bomb cyclone was actually a term used in the early 80s. Professor, there was a paper, Sanders and Giacomo, that first introduced the bomb cyclone. It just means that the central pressure of a storm drops 24 millibars or hectopascal in 24 hours, basically. And if it's equals that or is greater, then they refer to as a bomb cyclone. In 2018, as far as I know, the media picked it up. There was a bomb cyclone, off the East Coast. January 2018 brought a blizzard to a large part, and it's kind of been used to kind of, I guess, get clickbait kind of thing by the media. But I mean, so this one paper talked about it. Really wasn't used that much, I think. This, as far as I know, in scientific papers, storm dynamics is not my expertise, but that's what it is. So there is a technical, very technical definition. Doesn't sound very exciting, but these are the storms that most rapidly deepen. And when a storm at the time where it's rapidly deepening, it brings like the largest impacts: strong winds, coastal flooding, heavy precip. So it could be rain or snow. So, storms that are typically not deepening that fast don't bring as dramatic impacts. But I mean, we had this big weekend storm that wasn't a bomb cyclone.
There's a certainly discussion of ocean currents slowing down. Is there any possibility that the jet stream will stop or reverse?
No chance.
No chance.
Yeah,
No
no
chance.
chance.
It's good. That's something we don't have to worry about.
Yeah, no, that's very different. I'll quickly, it's more Jen's area of expertise, but I mean, I think as long as there's a sun, we'll have a jet stream, but that's all I'll say. Jen, what do you
And just elaborating on that, as long as we have a 6-month-long dark winter in the Arctic, which is related to the sun, nothing to do with greenhouse gases, the Arctic will always get cold in the winter. There will always be ice forming on the Arctic Ocean. And so the air above it will always be cold. And as long as the Arctic is colder than the areas farther south, that north-south temperature gradient will always create a jet stream.
Okay. And why really is the Arctic warming faster than other places in the world?
Well, I kind of described that already. I think it was that vicious cycle, or we call it a positive feedback loop, that the main reason there's a bunch of those vicious cycles that happen in the Arctic, but the easiest one to explain and the one that has the most influence on the rapid Arctic warming is this loss of sea ice. We've seen the Arctic sea ice loss in the summertime is now about 40% just in the last 40 years, which is an incredibly rapid change in such an important part of the climate system. And that ice loss, as a part of this feedback loop, is really what's responsible for the rapid Arctic warming. So as I said, you lose some ice, you absorb more heat from the sun into the water, that warms up the water, that warms up the air, that melts more ice, and you get this vicious cycle going. And so that's really sort of the main driver of the rapid warming in the Arctic.
Could you speak more on the relationship between the ozone hole improvement and the stratospheric temperature behavior in the southern hemisphere?
Yes. So ozone is also a greenhouse gas, meaning that it absorbs heat being emitted from the Earth's surface. But ozone is different in the sense that it also absorbs ultraviolet radiation from the sun. So when we had an ozone hole, it meant that less of that UV radiation was being absorbed because there was less ozone there. But it also meant that there was less absorption of heat from the Earth. And greenhouse gases also emit infrared radiation. So there was less loss of radiation to outer space. So now that the ozone is coming back, not every year, but most years, we're seeing it absorb more of the heat being emitted by the Earth. We're seeing more energy being emitted to outer space, but importantly, also more energy being absorbed from the sun. So during the winter months, though, you're really just down to the emission to space. And if you're increasing your amount of ozone at that altitude, which is very high up in the atmosphere, that extra loss of infrared radiation to space means that the air over Antarctica is overall cooling. And when that air gets colder, it means that the polar vortex there is getting stronger and the winds around it are blowing harder. So we're actually seeing an increase in the strength of the polar vortex there.
Great. The last question, I know that Judah has to go soon.
Yeah.
Wondered how, with the demise of NCAR, will this have an adverse effect on polar vortex research?
Why don't you take this last question, Judah?
Yeah, I also thought there was an AMAR question in there, which I'm happy to answer. But you know, I mean, yeah, NCAR is kind of the maybe crown jewel of research, atmospheric research, you know, in the United States. So its loss will be felt far, if it does go away, it will be felt far and wide, and be a big loss in research, including polar vortex research. You know, so yeah, I haven't worked that closely with NCAR scientists myself, but obviously they they're huge on model development. So, you know, our model, you know, the US models actually are behind the European and other nations actually. Taking away NCAR, we would just end up falling further behind in our, you know, the quality and accuracy of our models. But also just, you know, basic research would be greatly diminished, including that of the polar vortex.
Okay, I think we probably should wind up because we're after 5 o'clock, and I know Judah said he had to go. There are a number of people that have said a terrific program. Thank you all, and I add my thanks as well. I think that you did a great job, and we should certainly walk out with a better understanding of what's going on with our day-to-day weather now.
Well,
I
thank,
hope not only a better understanding, but also ammunition to talk to people who have skepticism, sometimes healthy, sometimes not. But, talk about this stuff. You have knowledge now that you can refute some of the silly things that are being said. So,
Yes, one of the comments was also that people look at the cold weather and they say, well, why are people claiming that the globe is warming up when it's so cold? So
yeah,
I think you've answered that one.
I was going to say, I mean, yeah. So a lot of times people say I'm very much involved with this, that, oh, there's 2 feet of snow in my backyard. Where's global warming? We need global, that kind of
Right.
sarcastic comments. I'm also often called, climate change apologist, where I'm trying to make it, so, oh yeah, it's cold. And I'm trying to find the reason how to justify that. But I do think it's really important, and I try to do that in my talk. We can make this cold, extreme cold, the heavy snow consistent with a changing climate, warming climate. I think that's what I think is very important, that people have come to an understanding that what we're seeing is not, we didn't know this 20 years ago, but that doesn't make it not true or accurate. And hopefully, I helped a little bit. I went fast through my 20 minutes, but you can understand how it can be consistent, that it's not refute climate change, and actually can be very consistent. That the cold, as I've said, the cold and the snow is not in spite of climate change, but it's actually, in part, not in part because of it.
Sure.
Hey,
Lori, did
Gary.
you want to pick up after
Yeah,
all
I
this?
have just, in addition, I wanted to thank both of you, Judah and Jennifer, for an outstanding presentation. I do want to remind people that on February 24th, we also have a upcoming Academy session. It's on the toxic legacy, and our own Walter Mugden will be presenting that presentation. And this presentation we will have up on the website. We've been recording it within a week or so. So share it with your friends and neighbors, and let's all get educated.